Alright, so what we want to look at right now is the concept of divisibility. And what we're going to work towards is we're going to think about numbers in how they multiply and how they factor. And so when we think of that, we've been thinking about numbers as being composed of additions, but we can think of numbers as being composed of multiplications. So for example, any number can be factored with a 1 times 2. And factors we list as all the different multipliers that come across. 1 times 3 is 3. 1 times 4 is 4. But 4 is also 2 times 2. And so we want to look at this idea of factorization. And what it's going to do is bring into play two types of numbers: prime numbers and composite numbers. And prime numbers are only factors of 1 and itself. And a composite can be made of multiple primes. And so 2 was prime because its only factors were 1 and 2. 3 was prime because its only factors were 1 and 3. But 4 is a composite. And we could write 4 in what we're going to call its prime factorization as 2 to the second power. Because there's the prime numbers that make up 4, and we write them in terms of powers. And so this is going to be what we're going to discuss for a little bit here. But to do that, what we need to do is we need to work on the idea of divisibility to understand what might or might not be prime. And this will help us with fractions, and divisibility in its own right will help us think of numbers in general. And so what we want to do is we want to talk about the counting numbers, or the natural numbers, which is the sets from 1, 2, 3, all the way up to infinity. And when we multiply natural numbers together, each multiplier is called a factor, and they create new natural numbers. And so these new numbers are composites of the factors. And so if we're building things by multiplication, then we can take apart by division. We can break back down. And so if A and B are in the set of natural numbers, right? So if A and B are in the set of natural numbers, then we say A is divisible by B if dividing A by B leaves a remainder of 0. And so divisible, or divisibility, is a property that says when we divide natural numbers there are no remainders. And so we write this as B divides A, where A is divisible by B. So we could write 12 divides 24, which is true because 24 divided by 12 is 2 with no remainder. But if we said 13 divides 24, that would be false, because 13 cannot divide 24 without a remainder. And so there are some nice divisibility checks that came across. So what we can do here is we can look at different numbers and see how they're divisible. So first off, on the number 1, right? 1 divides any number, right? And because it's always a factor, right, any number is divisible by 1. So 1 divides anything in the natural numbers. So, does 1 divide 5? That's true. Alright, because 5 divided by 1 is 5 with no remainder. Now, 2 divides things, even numbers, all even numbers are divisible by 2. How do we tell a number is even? Well, it's kind of nice is that it comes down to the last digit. If the last digit is divisible by 2, then the whole number is divisible by 2. I'll just use that for number. And so we can quickly check to see if a number is divisible by 2 by just concentrating on the last digit. So 713, right? Well, that's not true, because 2 doesn't divide the 3 evenly. But 2 does divide 9,848, because 2 goes into the last digit. And you could just pick some numbers and try the division out, and you'll see that if the last number is even, the whole number is even, and 2 divides any even numbers. Alright, if we look for divisibility with the number 3, look for divisibility with the number 3, what we can check is if the sum of the digits are divisible by 3, then the number is divisible by 3. So, for example, 381, well, if I add up the digits, 3 plus 8 is 11, plus 1 is 12, and 12 is divisible by 3. 3 does divide 12, right? It gives you 4 with no remainder. Well, let's double check this. So let's take 3 and divide into 381. 3 goes into 3 once, multiply. 3 goes into 8 twice. And 3 goes into 21/7 with no remainder. And so 3 does divide 381. The divisibility rules kind of sum up properties that happen because of our base system, but we put them into a shorthand that helps us find if numbers are divisible. So if something is divisible by 4, then the last 2 digits are divisible by 4. So, for example, 1,312. Well, the last 2 digits are divisible by 12. And so we would say 4 divides 1,312. Well, again, we're going to double check. 4 goes into 13 3 times. 4 goes into 11 twice. And 4 goes into 32 8. With no remainder. So it does work. I always found this one neat because you could make any number. Right? 9,832,424. And hey, that's divisible by 4. Because I just focused on the last 2 digits being divisible by 4. And so I come through and 4 goes into that twice. 4. I'm going to scroll up here. 5. 8. 1. 0. 6. Right. Sorry, I did that bring down the 4? 1 goes into it, 0, bring down the 2, goes 0 times, 24 and the 6. So no remainder. I always found that one odd. Well, another one that we get from counting is 5. Right? If we count by 5s, 5, 10, 15, 20, if the last digit is a 5 or 0, then the number is divisible by 5. Right. If we count by 5s, 5, 10, 15, 20, 25, 30, the pattern, right? A 5 or a 0, a 5 or a 0. So if I multiply all of these things out, I find divisibility. Now the next one, number 6, combines the rules for the divisibility by 2 and 3. And since 2 is a combination, or 6 is a combination of 2 and 3, we get the same thing. So let's look. 1, 1, 4. So this is even, so it's divisible by 2. And 1 plus 1 is 2, plus 4 is 6. So it is divisible by 3. So we can say this number, because it matches both rules, is divisible by 6. So we say 6 divides 114. Well, let's double check. Okay, so 6 goes into that once, and 9. And 6 does divide 114. Seven has an odd rule. So 7, double the last digit, and subtract it from the number that is the other 2. Or is the other digits. That result must be divisible by 7. This one sounds odd, so let's do it. An example. Let's do a couple of examples. So 672. So I'm going to double the last digit. So I'm going to say 4, and I'm going to 67 minus 4, because the last digit and whatever's left over, I subtract them, which is 63. Well, 63 is divisible by 7, so 7 does divide 672. Well, let's check. So 7 goes into 67 9 times, and 6. And we have no remainder. Well, let's look at another example. 105. So I'm going to double this, I get 10. 10 minus 10 is 0. And is 0 divisible by 7? Well, yeah. Because if I take 0 and divide it by 7, I get 0 with no remainder. Well, let's check 105. 7 goes into 10 once. Whoops, 105. Said 105. 7 goes into 10 once. 35, 5, 35, 0. And so that works. Divisibility rules are nice. Alright, got a couple more here. 8 is similar to 4. The last three digits are divisible by 8. Of course, this means that we have a deeper check to do, right? here. So 109,816. So we'll look at the last three digits and we'll go, well, are you divisible by 8? Well, eight goes into 816 once, 0, 2. And so this whole number would be divisible by 816. A neat little check you could do here is, well, 8 is 2 times 4. So this needs to be divisible by both 2 and 4. So if it's even and the last three digits, or the last three digits, the last two digits are divisible by 4, saying 3 because of 8, the last two digits are divisible by 4, then this is divisible by 4. And so I can say, hey, it satisfies both of these checks, so I know I'm going to get 8 back from it. And so we can kind of stack rules together. And so if we look at 9, 9 is a nice one, and I learned this when I was doing my multiplication tables, right? So that's 1 times 9 is 9, 2 times 9 is 18. Let's just write my times tables down here. And I'll go out, right, 27, 36, 45, 54. If we notice, the digits add up to 9. And we can say, is the sum of the digits divisible by 9? And so, for example, 9 times 12 was 108. Well, that adds up to 9. Right? 9 times 28. Let's do 9 times 28. 2, carry my 7. 18, 25. Well, 2 plus 5 is 7. 9. 9. And so we get the ability to add them up. In fact, we can multiply repeat this rule. So, for example, 1,629. Well, if I add up these digits, that's 7, 9, 18. And add up these digits, 9. And so 1,629 is divisible by 9. Well, let's check it. Goes into that once. Goes into that 8. And goes into that once. And so these are good divisibility tools. And 10, well, 10, if it ends in 0, it's divisible by 10, right? 10, 20, 30, 40. And so we have some nice divisibility rules that we can use to check if a number is divisible by another number. And there are more rules we can use, but we'll just focus on these first 10 that match each of the digits that we use. And so what we want to do is look at divisibility and how divisibility leads to the ability to prime factorize. And so, as I said before, a prime number is a number greater than 1. 1 is not prime. That has 1 and itself as factors. A composite number has multiple primes as its factors. And the fundamental theorem of arithmetic says that every composite number can be expressed as a product of primes in only one way. So fundamental theorem of arithmetic is all composite numbers can be expressed as a product of primes in a unique way. And so let's do this technique to find this from composite numbers. So I'm going to erase this here. And what we're going to do is called prime factorization. And I'm going to use number trees as the way of finding prime factors. So if we take the number 700, and what we want to do is we want to break it down into factors until they are primes. So factors we'll do in pairs. And so the first thing I'm going to see here is I'm going to focus on the divisibility rules I just went over. So it ends in 0, so it's divisible by 10. And so I have 10 as one of my factors, and I have 10 times 70. And so I'm going to continue now to break down each branch in my tree. So 10 can turn into 5 and 2. Well, 5 and 2 are already prime. Now 70 can go into 10 and 7, and 7 is prime. But 10 can also be 5 and 2. And so I can write this entire number as 7 times 5 times 5 times 2 times 2. Remember back when we started this module's lecture, we talked about exponents. And so our prime factorization for 700 is 7 times 5 to the second times 2 to the second. And this is a way of writing 700 only in prime numbers. And prime factorization, since this is a unique way of writing numbers, will become a very useful tool for fractions and dividing. Right? If we have fractions, I'm making this up in my head, well, any number over itself is 1. And I can break up a fraction into its components. And so let's see, 2 times 93 over 2 times 134. But 93 is divisible by 3, so that's 2 times 3 times 31. And 134 is divisible by 2 again, so 2 goes into that 6. 67. And so these 2's would cancel or become a 1, and so I get 3 times 31 over 2 times 67. But notice what I did is I broke this down into its prime factorization so that I could remove wherever I saw a prime over top of itself. And so this is going to be a tool that works for us. And one of the first ways we use primes as a tool is in the greatest common divisor. And so we want to find a greatest common divisor of 2 or more numbers we write the prime factors of all of the numbers. We select all primes common to each number, choosing the smallest exponent. And then we form the product of these numbers. And numbers that only have one as their greatest common divisor are called relatively prime. And I'll use the example from the book, 5 and 26. Well, 5 is prime, so its factors are 1 and 5. And 26 is 1, 2, and 13. Well, the only commonality here is 1. So these are relatively prime to each other. Well, let's find a greatest common divisor. And so we'll start with a factor tree. So let's take two numbers. We'll take 216 and 234. And we want to find the greatest common divisor, the largest number that they can be divided by, that they both share. So I'll write the prime factor tree. Well, this is even, so 2 times 108, that's 2 times 54, and that's 2 times 27, and that's 3 times 9, which is 3 times 3. So grab everything on the end of the tree, and so I'm going to get 2 to the third power, and 3 to the third power. And so 216, and its prime factorization is 2 to the third power times 3 to the second power. I'm going to do the same thing to 234. Or wait, that's 3 to the third power, right? There's 3 of them, 1, 2, and 3. 3 to the third power, my bad. And so 234 is 2 times 117. And 117, let's see, 8, 9, that's divisible by 3. So it's 3 times 3, 9. Well, that's also divisible by 3. So it's 3 times 13. And so the prime factorization of 234 is 2 times 3 to the second times 13. And so now my job is to find the things that are common. Okay, so they both have a 2, and they both have a 3. And I take the smallest exponent. So the smallest exponent of the 2 is just 2 to the first, and the smallest exponent of the 3's is 3 to the second, or 2 times 9, or 18. And so 18 is the greatest common divisor. I can divide both of these numbers by 18. And that is the largest factor that these two share. The greatest common divisor is the largest number that two numbers share. Well, another thing we can do is in the opposite direction. The least common multiple. And you'll notice a lot of times in mathematics we'll do a forward and backwards idea. So breaking a number down into its largest shared factor gives us the greatest common divisor. The least common multiple is a natural number that's divisible by all the numbers we have. So if I give multiple numbers, the smallest number that has the factor form. In fact, what we're kind of looking for is a number that has the list of numbers in them as part of its construction. So to find a least common multiple, we again write the prime factorization. Of each number that we're going to do this for. Just use that for number. Select every prime factor that occurs to the greatest power. Select each prime, not each prime that's common, but each prime that occurs to its greatest power. And then we form the product of these. Alright, let's look at an example of the least common multiple. So if I want to find the least common multiple of 144 and 300. So I'm going to prime factorize both of these. So I'll start with the 144. That's 2 times 72, which is 2 times 36, which is 2 times 18, which is 2 times 9, which is 3 times 3. So there's what? 1, 2, 3, 4. So that's equal to 2 to the 4th times 3 to the 2nd. Now 300, let's see here, 3 times 10, or times 100, which is 10 times 10, which is 5 times 2, and 5 times 2. And so 300 is 2 to the 2nd times 5 to the 2nd. Oops, and the 3. Let me get this in proper order. I have a lone 3 in there, and then 5 times the 2nd. And so these are my prime factors for 300, and these are my prime factors for 144. And so now I take each that occurs to the greatest exponent. So I'm going to take my 2 to the 4th, 3 squared, times 5 squared. And so 2 to the 4th gives me, let's see, 2 to the 4th is 16 times 9 times 25, or 3,600. And so the least common multiple of 144 and 300 is 3,600. And let's look at what we can do with least common multiples. So this does a very useful thing. Well, they all do useful things, but this one has a neat one. So a movie theater runs its films continuously. We have an 80-minute film. So I'll say the time for the first film is 80 minutes. And then we have a time for a second film, which is 120 minutes. And both movies start at 4 p.m. And so we want to know how long until they both start at the same time again. Because we'll know the first one will end in 180 minutes, but the other one's still going. And so we want to see how often these will repeat. Well, this is actually asking for the LCM of the times. Because if this is running for 80 minutes and this is running for 120 minutes, the next time they're both at the same time, the time in here, whatever time has taken place, well, it's going to be some multiple, some n times 120 minutes, and some m times 80 minutes. But these two things would equal. And so we need to find the least common multiple. That would be the time that we would need. So let's find the least common multiple. 80 gives me what, 2 times 40. This gives me 4 times 10. This gives me 2 times 2 and 2 times 5. So I get 2 to the 4th times 5. Now for the 120 minutes, what do I get? 10 times 12, which is 2 times 5, which is 3 times 4, which is 2 times 2. So I get 2 to the 3rd times 3 times 5. And so for the least common multiple, I'm taking a 2, a 3, and a 5. I'm going to take 2 to the 4th times 3 times 5. Or 16 times 3 times 5, which is 48 times 5, or 240 minutes. And so in 240 minutes, these films will be together. What is 240 minutes? It's 4 hours. And so they'll be running at the same time again at 8 p.m. This first one will have played twice, while the second one will have played 3 times. And so least common multiples are a way of calculating when events can occur in multiples of each other. Alright, and so we've looked at divisibility and factorizations and what we can do with factors. We've also solved some problems with them. We'll continue to explore these ideas.